Hello, this is Math2270 coming to you from the College of DuPage during the summer of 2020, and this is the conclusion of the lecture called Eigenvalues and Vectors Done Light. When last we left off, you were working this problem. I hope you finished it, but if not, you know what to do. Let's see how you did. Well, so we have to calculate this polynomial. So it's the determinant of a minus lambda I. We do that and we calculate the determinant. We get this one times this one minus this one times this one. So that's what we get. We simplify and we have lambda squared minus 2/3 lambda plus 1/9, which factors, and you see we have a double root, a root of multiplicity 2 of 1/3 for this. So we take a minus lambda I times these, and this is for the lambda that we had, and we get equal to 0. And if you notice, you will see that both of these rows really lead to the same thing. So we'll take the top one, and we get this, and that means that a to 2 is equal to 2/3 a to 1. So we can write it this way. And if we take a to 1 to be 3, that'll make that into a 2 and that into a 3. And so that's all good. Let's look at example 3. Here's a different matrix. You know what to do. Let's see how you did. Well, you do the characteristic polynomial again, do the calculation, but this time you find out that the roots are -1 plus or minus 5i. So we have an imaginary component for this solution. And it works the same way though. So this is -4 minus lambda, this is 2 minus lambda, and we knew a to 1, a to 2 equals 0. And we get this when we simplify all of that. Now, it might not be obvious, but these two really are the same ratios. What will happen is that here the ratio is going to be minus 1/2 times 3 plus 5i. And over here you would get the same thing if you multiply top and bottom by the conjugate of the denominator as you would. Okay, so we have that, and we'll use the ratio of 1 is to 2 is this, so that's what we get for that. And that means we can use the bottom one. I guess we could use either one. So 2a to 1 is equal to minus 3 minus 5 halves a to 2. And that means that this is what we get. And so we can put this into this, and we can take a to 2 to be 2. And if we do, that will cancel out nicely there. And this is what we get for our eigenvector. So this eigenvalue is paired with this eigenvector. But we also had the complex conjugate. The calculation is going to be much the same. -4 minus lambda, 2 minus lambda. We do all of the calculations and work through this. This time we end up with this. If we take a to 2 to be 2 to be our solution, and if we look back we say, oh, this is the complex conjugate of the other solution that we have. And so to summarize, this is what we have. We have the two eigenvalues and their two eigenvectors, and here you can see that you got the plus in there, so that is the complex conjugate. Now, we didn't prove this, but it truly is a fact that if A is any n by n matrix with only real numbers, and lambda 1 is A plus BI is an eigenvalue with eigenvector eta 1 superscript, then lambda 2 equal lambda 1 bar equal A minus BI is also an eigenvalue, and its eigenvector is the conjugate of the one we had before. And we can use that in our calculations. And that even could have shortcutted this calculation a bit. All right, here's another example. And now we're doing a 3 by 3. Works the same way. You know what to do. Let's see how you did. So we get our characteristic polynomial, we get this, and when we find the roots, we realize as factors, you've got a single root at lambda 1 is 2, and you've got a double root at -1. Now this time we do need to solve this a bit because it's not going to be obvious from the beginning. And so we set up the equation. Again, we're doing the this is going to be, it is a minus lambda I is what we're looking at here. Times these are going to be 0. But when we reduce this, do some row reductions, we will end up, I guess we'll do the row reductions to get down here. This is what we get. And so you see that this row will tell us that, the first row will tell us that a to 1 minus a to 3 is equal to 0. And the next one will tell us that, the next row will tell us that a to 2 minus a to 3 is equal to 0. So all of those are equal. That means this is what we have. And if we take a to 3 to be 1, our eigenvector is 1, 1, and 1. Now for the next eigen value, -1, you need to solve this, and you see what's going to happen here with this. You're going to have the sum of the 3 is equal to 0, and that means that a to 1 is equal to minus 2 minus a to 2 minus a to 3. And so when we put that into our form, we get this. And you remember that we can't have 0, so a to 2 and a to 3 cannot be 0 at the same time, or else that would give you 0. But they can be 0 separately. So here I take a to 2 to be 0 and the other one to be 1, and here I do the other way about. But notice I get 2 different vectors that are eigenvectors for the same eigenvalue. So now we see that that happening, and these are independent because they're not multiples of each other, because the zeros are in different places. So here are the eigenvalues and eigenvectors for this matrix. I think we're ready now. Now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other.